Hi everyone, welcome to another LeetCode algorithm problem. Today we're going to look at LeetCode 2415, which is all about reversing odd levels on a binary tree. So we're told that we're given the root of a perfect binary tree, and we need to reverse the node values at each odd level of that tree. And we're given an example here of what it means to reverse the levels in the nodes in a level. This is kind of like any reverse operation that we've ever seen, looking at strings or trees or numbers, doesn't really matter. Whatever is first should end up being last, whatever was second should be second to last, and so on. And important, we're told that we got to return the root of the reversed tree. So we can't just change the root in memory. We've got to actually return the root to the checker in LeetCode. And we're told a definition of a binary tree being perfect. So what this really means is that every node, it either has two children or there are no children on the node and then it's a leaf. Another way of saying that is that all leaves are on the same level, so there are no branches that are longer than others. And we're told that this definition of level comes from the number of edges along the path between the node that we're looking at and the root node. So really here the root doesn't have a level, or you could call it level 0. And the first level is these two nodes right here, 3 and 5, because there's one edge from the root node to that node. And then these four values down here would all have a level value of 2 because all of them have two edges going to them. So that's going to be important as we work on this problem. With that information, I think we're ready to do some visualization and exploration and start solving this problem. Over here, I've pulled up some code from the LeetCode website. This is the definition of a tree node that we get to work with. And then I've added a lot of code here, but none of this is needed to solve the problem. Again, like in a lot of my videos, I've got some code here to help me visualize things, but you don't need this to do the solution. This is just to make me printing out values easier. I can tell you what all this does real quick, but again, not part of the video. You don't really need to learn it. Basically, I've got another method on tree node that allows me to print the layers of the tree node in the order that they show up. And then I've got a function down here that I can put in some simple lists and create tree nodes out of that list. You can see that I've used this here. All of this basically gets me to the point where I can do something like this right here. Let me make some space so I can scroll down. Oh, that's not right. Space underneath this. Okay. What this allows me to do is it allows me to create a tree node very easily and then print out the layers also very easily. All right, now looking at this, I want to start visualizing what we want our solution to look like. Remember this root value right here, the very first node in the tree has either no level or a level of 0, so we're not going to reverse it. But when we have our function that works, we hope that 3 is on the left and 2 is on the right, and then 4, 5, 6, and 7 should remain the same, and then 8 through 15 should get swapped. So keep that in mind as we go through some code here. There are a lot of ways that we could try and solve this. Generally with tree problems, we can either use a depth first or a breadth first solution. I prefer depth first, so that's the way I'm going to tackle this, but please know there's a lot of ways to solve this quite efficiently. So I want to set up the skeleton of how I want to do this, and we can talk about the intuition and roughly what we want to do here in this problem. So I'm going to create some function called depth first search. Don't know exactly what it's going to do right now, and just lay out the rough guidelines of what we think we might need to do. So we'll have a function called DFS, and as with a lot of these DFS recursive problems, we need a couple things. We need to handle basically like our null / base case. We need to do whatever we're supposed to do. So do something, right? Change data, move values, do whatever the problem's asking us to do. And then we need to recurse. So with this problem, the null and base case should be pretty easy. We're going to have some kind of input, and we need to just make sure that it isn't null. If the value isn't there, then we need to return none. And this is going to happen when we get to a leaf node Remember our definition of tree node up here, initialized with left and right are equal to none. So when we get to a leaf node, they're going to have none value. So we need to do some kind of null check here, but we don't know what our inputs are. So with this problem, we should assume that we're going to at least have one input, some way of getting through the root and processing the whole tree. I'm going to go ahead and give something away, which is that I think this works best when we have two different node values put in here at one time, two different arguments for two different nodes, and I'm going to call them L and R. And then there's some kind of state that we need to measure, right? Because we've got to know what level are we at inside the tree. Because if we're at an even level, we don't want to do anything. When we get to our do something step, we need that logic to not execute. So I'm going to keep track of that state of level, and I'm going to call it level. So on our null or base check, we need to make sure that left and right aren't null, aren't none, aren't nothing. But we have a perfect binary tree, so actually we can really just check one of these. What we can do is we can say if not L, then we can return none. And then for our do something step, so we've got a binary tree. We really have two methods that we can change. We can either change values or we can change left and right pointers. With this problem, it may be tempting to change the left and right pointers because when we're doing a general reversal of a binary tree, that is the easiest way to do things, and it creates the simplest recursion update. However, I don't think modifying left and right pointers here is going to help us. And the reason I don't think that is, imagine what we do with root here if we change the pointers from 1 to 2 and 3 to swap them. There are downstream effects. So, I mean, let me just show you. So we've got root up here, right? If I take root.left and root.right, and I swap them, so root.right is equal to, we got root.left equal root.right, and root.right equal to root.left. And then if I go ahead and print root again, look what happens. We do swap 3 and 2 like we want, but also we end up swapping 6 and 7 and 4 and 5. So we would then have to go into this layer down here and kind of fix everything and get it back in the right order. And then we have an even bigger mess down here. We've got to fix another layer. So this problem can actually be done more efficiently if we swap values instead of pointers. So if we just choose to swap the values of 2 and 3, but keep the pointers downstream the same, we don't have to do any cleanup. We know that the action that we take has no downstream effects. So let's go ahead and do that. So we know that left and right are not the children of a leaf node. So what do we want to do? We need to check the level. So if level is even, we don't want to do anything. If it's odd, we do. So basically, we can use the modulus operator here. And if level modulus 2 does not equal 0, if it's not even, if the level value that we're managing is not even, then let's go ahead and do something. And what we can do is we can take our left value and our right value, and we can swap them. So we can have left value equal to right value, and then right value equal to left value. Now that we've swapped the values, the last thing that we need to do is we need to recurse. We need to take a step forward as we're trying to solve this problem. We know what the signature is going to look like for that. We're going to have depth first search on 2 objects and then level. And what those objects are going to be is they're going to be another instance of left and right. We just need to make sure that they're consistent instances. And so what we need to do is we either need to work from the inside of our string, not a string, the inside of our layer in our tree node, or we need to work from the outside. Meaning, on this example, level 1, reversing those actually let me point to this version up here since it's in the right order. Reversing these, it doesn't really matter because it's only 2 nodes. But when we get to a larger layer of the tree node, we need to be consistent. Do we either want to begin switching objects from the outside in, or do we need to work from the inside out as we switch objects? I'm going to say, just because for me it's easiest to think about, I want to work from the outside in, but you can do this either way you want. So our first recursive call is we're going to take left, and we're going to access its left pointer, and then we're going to take right, and we're going to just R. We're going to take right and access its right pointer, and we're going to keep track of our level, but we're going to increment it. So we're increasing our level. Why? Because we're going down a level. And we're doing a new recursive call here where we're going to the current left pointer's leftmost node and the current right object's rightmost node. And that'll take care of the outside of our level. And then we need to capture what's on the inside also. So we need another recursive call, this time for what is on the inside of these two objects. So we can take the rightmost object in the left and then the leftmost object in the right and still increment the level. And how this is going to work is that the recursive call for the outside objects will always go first. So this binary tree will actually get reversed from the outside in. So 2 and 3 will get swapped. Nothing will happen on this layer. And then 15 and 8 will get swapped. And only once that has happened will we ever access the second recursive call and begin to take care of objects that are inside the objects that are all the way on the outside. You can switch these. It doesn't matter as long as you're consistent and as long as you swap things in the right order. That's actually all we need here. Now we just need to call this function. So we want to start it off, and to start off depth first search, we want to take our root and we want to input what's on the left, what's in the right, and we need to initialize a level value. And since we're starting with what's from the left and the right of the root node, we need to make that level 1 because we're accessing one edge to get to each value. So I'm going to put in a value of 1 here. And then finally, just so we can see what we're dealing with, not part of the solution, but just to visualize it, we can look at print by layer on this and see what it looks like. I need to get root back in memory because we altered it down here. So get a new version of root, and then we can test our function. Okay, and this looks right. Yeah, we've got 3 and 2 swapped instead of 2 and 3, and then this whole layer right here, this whole level, has also been reversed. Here you can see I've taken the code we just wrote. I stripped the code comments out and left some spacing for readability. Beyond that, nothing has changed here outside of an extra return statement. So in the wrapper function, outside of depth first search, we do have to return something for the LeetCode checker, and that thing we have to return is the root node in the input object. So that's what I've done here so that the LeetCode checker can go through things. And when it did, we got a correct solution. We got a really fast runtime. Memory management, not so perfect, so there's probably some tricks that can be learned to make this better. It may be that other solutions like the breadth first search solution, for example, is more memory efficient because there's less stack management. A lot of that can be done with queues, but depth first search is totally an accepted solution, and it performs totally fine for an interview. And I think it's pretty elegant. Well, I hope you guys enjoyed the video. I hope you learned something, and I'll catch you soon on another algorithm problem.